Okay, but let's continue. We have still a couple of topics to cover. So next, what we will do is to kind of see how we can make spatial joins. So what we just did was basically that we kind of make this kind of spatial selection, but basically quite often you actually want to join some information between the two different layers, spatial layers, and what that operation is called is spatial join. So let's continue and that. What we will do here is basically that we will see and work with the population data from Helsinki region, and we will basically see and make a spatial join between the population layer and the addresses, if I remember right. But yeah, let's continue. So let's start by downloading this kind of data set here. So I think it should come just by clicking with left. So what we have here is this kind of zip file called väestötietoruudukko. So this kind of population grid that contains a shape file, and let's take a look. So what I will need to do now is to extract it here like this, and now what I have is exactly this kind of shape file, and we will read that into Spider. Again, I will create a new script, import GeoPandas as GPT. Let's save this here. Lesson 3, Spatial Join. So let's do this now. So first of all, what we want to do is, again, well, we have that new shapefile, so let's read it in. So let's say file paths, and the file path to our file is, well, it's this one. So again, the same thing. So I want to copy and paste this shapefile file path here, and then I want to read the data. So how I will call this is pop. It's population data that we have here, so I call it pop as population, and read file fp, and in this way we should be able to get the population data inside, and we can take a look. What do we have? So we have this kind of data frame, geodata frame, where we have the polygon, so it seems to be some kind of layer with polygons. Then we have some attributes. The important one here is basically this asukkaita column, meaning inhabitants in English. Then we have some other attributes, but what we are interested in here is mainly this kind of how many inhabitants we have. What we could do to make this more easy to read and understand, so this population grid is basically from year 2015. So let's change the name of that column into pop15 so that it's more understandable for those who doesn't know Finnish. So rename columns. You have done this already before, but it's good to kind of do it and repeat it a bit so that you can remember. So how we were able to rename columns of data frame was this rename function, and inside here we basically specify that the columns equals to, and then we have this specific data type that we could use to rename called dictionary, which is a basic data type in Python, and this works so that we basically specify the old name, which is the asukkaita, which is this one, and then we have a column, and then we specify the new name for our column, and I want to call it pop15, which is basically population in 2015. So let's do this, and now we can check the columns, and indeed now we have the pop15 in here, and then we have the other ones as they were before. We can basically, we don't need those other columns, so we can actually drop those out. So basically what I do is that I just copy and paste these from here. I create a column, drop columns, so drop cols equals to, then I create a list of those columns that I want to drop, so I just copy and paste it here, and now I have a list of all those that I want to remove from my geodata frame. How I can do that is basically that I say that pop equals to pop drop. So this drop is quite nice function to remove columns. Use it carefully. You don't want to remove something important, but basically it can be used. And basically there are this kind of parameter called labels. So what labels do you want to drop from your data frame? Well, we want to drop those that I specified in this drop calls list in here. And then important thing to specify here is to say that the axis equals to 1. So we want to remove those kind of columns instead of rows. So again, something specific to pandas that needs to be specified. But now when I didn't specify that yet, or run. So now we should have a population, or this pop data frame, only with the pop15 attribute and the geometry. So let's continue working with this one now. Then what we want to do next is that we want to again use those addresses that we geocoded. So again, I just copy and paste these from the other. So we have the shapefile here, and I just copy and paste it here, addresses shapefile, and then I basically read that in. Addresses equals to gbd.readFile addresses fp, and then I basically read it in, and again we should have those addresses like this. So they are points. One really important thing to now check is the geometry and the values that we have here. So what you can see from the points is that they are basically latitude and longitude values, or actually longitude and latitude values, and here the polygons, they are something else. Let's see what is the coordinate reference system. So it seems that we actually have some specific coordinate system to Finland in this one. So it is ETRS 35 projection, if I remember right. So it's a metric projection, whereas this is basically decimal degree. So what we need to do in the beginning is really to convert those addresses into the same coordinate system where those polygons are. So let's do that first. So reproject the addresses to same projection as population data frame. So how we could do that was that we can say that addresses equals to addresses to CRS. And what is the CRS that we want to use? Well, it is the same CRS that the population data frame has. Let's just create a copy if this doesn't work, just to okay, let's see, pop.crs. Okay, let's try another way. Say addresses geometry equals to addresses geometry to CRS, maybe like this. No arguments in English list. Okay. Let's do a little bit of testing now. Oh yeah, it seems to be this EPSG code 3879, so we can do it using that information. So from final.crs import from EPSG, so we can use that EPSG equals to EPSG, and it was 3879. Let's see if this now works. Says either C or need to go and read my own materials. What is the problem in here? EPSG equals to.
Is it not possible at the first time?
I think it should hopefully work like this now. Okay. Addresses.crs. That's the reason. Okay. Yeah, so it doesn't have a coordinate reference system defined, so that was the reason why it didn't work. So what we need to do first is to say that addresses.crs, so give some coordinate reference system for the geodata frame. Well, now we can take advantage of this from EPSG function that we specified, and the coordinates were latitude and longitude, so it is this WGS84 where the EPSG code is 4326 that I just happen to remember by heart. So now we should have this defined, and now we should be able to do the projection conversion. Actually, I will show you and do it like I wanted to do it in the beginning, because this can be quite handy in many cases. I just can do it like this. So that basically what we are using as an input to this toCRS function is that we specify that take this coordinate reference system from this layer, so the population data frame here, and feed it into here. So this is quite handy because you might want to, as I have said in the previous lecture, that make sure that the layers are in the same projection. In most cases it might not matter which the projection is exactly, but you need to be sure that they are the same. So you can basically set one of the layers or the data frames that you have as a baseline and basically convert every one of them into that one. And that is quite kind of a good way to make sure that every single geodata frame is having the same projection in there. So now we have finally the addresses and they are in the same coordinate reference system. So now the geometries in the points are the same, or they look the same as in this pop data frame. So the numbers look quite similar, which is good. One last thing that we need to do is to specify the CRS code. So still at this point our coordinate reference system information, it updated it. Okay, that's good. Well, no worry then, this is something new. So it's okay. So now we have the same coordinate reference system here. Then to the actual work that we want to do. So what we wanted to do in here was that we want to join the kind of, not here, we want to join the information between these two layers. So the aim is to find out how many people live in a polygon that contains an individual address point. So we want to join the attributes from the population layer into the point layer that we just dealt with here. So let's see how we can do that. So what we want to do is indeed to make a spatial join, and we want to join to these addresses information from the population. So kind of take the information from that polygon where the point is located and take that information back to the point attribute table or the geodata frame. So how we can do that? Let's create a new attribute called join, and in this GeoPandas GBD dot there is this kind of function called sJoin. Is it actually here? Yeah, it is here. So this is basically saying spatial join, and what we have here is the left DF, so left data frame, right data frame, and how do we want to make it is to make it an inner join, basically keeping only those records where we found the matching kind of features, or if you have outer, then you will have all the features from both of the data frames, even though they are not kind of matching features found. And then we have this OP parameter. So in this we basically define, do we want to make do the intersect, do we want to make contain kind of comparison, do we want to make within, or what kind of measure we want to actually do for doing the spatial join. So what we do here is that we want to do the spatial join between the addresses. So that is our left data frame, and then our right data frame is this population geodata frame. And how we want to do it? Well, we want to keep only those where they are matching, so we do the inner join. And then what is the type, query type that we want to use? So we want to do the within. So basically those points are within the population grid. So that information should be added here. And let's run this. Didn't take too long, and let's see what do we have now. So what we have is indeed that we started with the addresses, so we have all the information from the addresses here, but then we have also some index, right? So this is specifying what is the index of the polygon on the right data frame. But the important stuff here is that we now got the attribute pop15 from the other geodata frame. So indeed what we did here was we did a simple spatial join between the layers, and we got information from one layer to another one. And now we can basically, we could save this into a shape file, for example. Well, what I want to maybe do now is to take a look of what do our data look like. So I will create another map. So I will import the matplotlib library like this, and then I will just create a plot. So we can say that join dot plot, and what do we want to plot? So there is possibility, I don't remember if we have used this before, but there is a possibility in the plot to specify that use this column to make the coloring of those geometries that you have on the map. So we said that what I want to use as the kind of attribute where the kind of color scale is drawn from or drawn upon is this pop15 column with the population and kind of numbers. Then I can specify what is the color map. So now thinking of when you do maps in Quantum GIS or ArcGIS, we are going into the Symbology layer. So we specify the color map. There are many different kinds, but we can use, for example, reds. So they are going different variations of reds. Then what we can specify is the marker size. This you show already before. We can say that the size of the point should be 7. Then we can classify our values based on different kind of schemes. So for example, natural breaks is quite often used. So we can specify with parameter scheme that I want to classify my values based on natural breaks. Again, something that you usually do when doing the kind of visualization in Quantum GIS or ArcGIS. Then I want to say that draw the legend as well. So I can specify that legend equals to true. And in this way, we can create a plot. And it doesn't work because I misspelled CMaps. It's CMap. Now we have something like this. So indeed what we now have here is that basically we had the, let's create a quickly, so pop.plot and column equals to pop 15. So the original data, so where does these colors come from, is from the population layer. And basically the more people are living under this point, so the more darker red the color is. And this is how you can get this kind of map as an output, where we actually created a spatial join first and then this kind of simple map. Let's see if this takes now forever to do this. Maybe I don't want to wait for too long, but okay. Interesting. This is something that you might need to do sometimes, to restart the kernel of the IPython if you do something like I just did. So I wanted to quit the drawing of the map before it actually ended. So, but anyway, so yeah.
Could you show how you've written the scheme? Because I have invalid scheme. I have written natural underscore breaks.
Yeah, so it's like this. So scheme equals to natural underscore breaks. Huh. Let's see. What version of GeoPandas do you have? So. Oh yeah, you have, and I guess you have. Let's see what I have. Well, actually, I have older one, but I think actually what it uses under the hood is this PyCell library. So actually, if you say that import PyCell, does it do anything?
No, it didn't give any error.
Okay, so it
says module PyCell has no attribute.
Okay. Okay. Well, it doesn't have. But I think it might be something to do with the different versions of PyCell and the GeoPandas that we have in the computers. So this is something for the next year. There are so many different computers with so many different setups, so we have been struggling with the installations and stuff. So maybe next year again we will be sticking with the cloud computers, because everything works so much easier that way. Did you have a?
Yeah, maybe I will just try to install PyCell using pip install PyCell.
Yeah, it could work. Yeah, it should be also in Conda if I remember right, but we can check it out later. But anyway, the scheme, so if there was some available, so you can choose one of, yeah, equal interval quantiles. Yeah, so this is just one of them, which is of course quite nice kind of scheme. Unfortunately, it's not included there, or didn't work. But anyway, just that you know that these kind of schemes can be used. Okay, then one last thing, if you still have some power in you, the nearest neighbor analysis. So this is the last topic that we will go through. So the idea is to find the nearest from multiple points, find nearest one to this point where I am now. So really kind of often needed spatial operation. So again, we are working with Shapely, and let's start from the scratch. So from Shapely import, well, Shapely geometry, import point, multi-point, and then I save this. Nearest neighbor. Let's do this here. So so we are working with the Shapely geometries as we usually are, but in Shapely, so the kind of function that we want to use here is called nearest points. So in here Shapely.ops we should have this kind of nearest points function. It's from Shapely version 1.4 onwards, so I hope everyone has newer than that one installed. At least I do. So we can import those, and if they come nicely, you should be alright. So the first thing let's check like the basic principle how we can do this kind of nearest point analysis. So let's just create a couple of points. So let's say that we have this origin point. So this is the place kind of where we are looking at. And let's create a point with just some coordinates like 1 and 1.67. There are some coordinates in some projection. And then let's create a few destination points. So these are the ones where we want to find the closest one from. So I say that dest1, comma dest2, comma dest3, like this. So it is possible to create multiple variables with one line basically, and this is how you can do. So you just separate them with comma and then say that the first one, so dest1, will have coordinates 0, 1.45. So this will go to the dest1. So the next one will go to the dest2. Let's give the coordinates 2, comma 2. And the third one will have 0, 0, comma 2.5. So in this way we created 3 different points, and when running this we should have these dest1, dest2 and dest3 points in here. Yes, they all look like Shapely objects when printed them out. So we want to find out from this point that which one of these is closest one to this one. So how we can do this is basically that we want to first combine these 3 points and make them as a one single feature as a multi-point object basically. So we need to do that first. So we can create a multi-point object. So we can say that I have this variable called destinations. So they are all these 3 combined into this one bigger multi-point object. And this multi-point takes as an input parameter a list of points. So in here we just specify as a list those points that we just created. Dest1, Dest2 and Dest3. And when we execute this, should have destinations, and they look like, I don't know if you can see, but they look like these 3 points in here. So now the idea is to check that from these features, which one of them is closest to this oric variable here. So we take advantage of this nearest points function. So find out the nearest geometry. So I create a variable called nearest geoms equals to nearest points. So using that function, and then in the parentheses I specify G1, G2, so geometry 1, geometry 2. So the first geometry is the oric, and the second one is now this multi-point object where we combine all those 3 that we want to compare. So it is the destinations, and this is basically it. We can see what we have as a result. We need to create this oric first. Hopefully now it works. So now it did and execute it, and now we have these nearest geoms. So let's see what do we have inside there. So indeed it seems that we actually have as a result shapely objects. Let's see what those objects are. So I just create well, I don't need to create, I just print out the first one of those. So nearest geoms 0, so this is the first one. So let's see what do we have there. Well, we have point objects at those coordinates, and here we have the oric variable with the exact same coordinates. So indeed it seems that what this function does is that as a first item it actually gives you the same coordinates that was fed into the function. So it is this oric. So of course that is the closest point because it's the point itself that is compared to it. But the second is the actual one that we are interested in. So the nearest geoms at index 1. So let's print that out, and it seems that okay, this 1.7041, so it seems that the first point that we created, so this destination 1, seems to be the closest one to that point that we have here. And by looking at the coordinates, well, it's not maybe that obvious, but yeah, makes sense in a way, as here we have 0 and 2.5, 2 and 2 and so on. So it indeed seems to be the closest one of these three ones. So this is the basic kind of logic that we can use to do the nearest point kind of analysis. But of course this is again not that useful, but when we take this approach and take it into GeoPandas and work with full geodata frames, then we can actually do some useful stuff with these functions. Unfortunately, at least I don't know that this nearest function is not implemented in GeoPandas, so that you could just use it as in a similar manner as, for example, that Spatial Join that you did. So what we need to do is kind of write a function to do this in GeoPandas, and let's do that now. So the idea is that we basically want to check from the from those Helsinki districts that we just saw in previous tutorial, we want to take the centroids of those areas and find out from these addresses which one is the closest address to each one of those centroids. So that is the kind of idea. I have written you a function that we will use, which is basically it will find out the nearest point and return a specific value from the other data frame that we are interested in. And I will just basically copy and paste it from the web to here so that I don't do any stupid mistakes. I will just quickly go through what we have here. So in this, so how we will use this function is again this data frame.apply that we have used a couple of times, where we actually use our self-made functions to run stuff. So the kind of approach that we use here is similar. So the first item here is the row that we feed into the function. Then we have different parameters here. So we actually have quite plenty of different parameters. The first parameter here is the geometric union. So as you saw, when we made this kind of nearest point comparison, we actually created this multi-point. So this geometric union basically is same thing as this multi-point here. So you need to make a union of all those geometries in your data frame that will be then compared to. Then we have two different data frames. So we have data frame 1 and data frame 2. So the data frame 1 is, for example, the addresses, data frame 2 is the polygons, and then we have different, so by default from which column the geometries are read when this function is used is the column called geometry, which is by default the one that GeoPandas uses. And also we have for the data frame 2 same parameter. So you can basically specify also different column names for this function to use to actually make the comparisons, which is useful because I will just show you soon why it is so. Then the last column here is the SRC, so source column. So this function works in a way that we basically find out, so you have data frame 1 and data frame 2, and you want to have certain column from the second data frame and take that information back to the first one. So this source column basically specifies that what information you want from there. You could of course modify this a bit to get, for example, all the attributes from there, but for this purpose we are just taking one column. So let's see how we can do this. What I will use is basically I want to use the addresses here, so not this one. So I want to use that shapefile, so we are again working with the same files, so I just copy and paste that. And then the other one is not that one, but this one, so the polygons. So it is the KML file that we are reading in, and we are taking the centroids of these polygons to find the nearest point. We'll just take this way, and then, well, I just copy and paste a couple of things from here to here. So just import shapely speedups, and then I specified the configuration for GeoPandas so that it can read the KML files. So that was that. And then we just read the addresses and read the polygons like this. So I just run these to check that everything works. Okay, no errors. So now we should have the data in. So let's say data.head. Yes, we have the data, and the geometry seems to be in latitude and longitude. Let's check that the polygons are the same. Yes, indeed, they seem to be latitude and longitude. So we are good to go. We can actually do comparisons. And the next thing what I want to do, as I said, I want to basically check from these addresses. So the data they are points, as you can see from here. So I want to find the closest points from these ones to these polygons. That looks like this. So for each centroid of these polygons, find out the nearest one to each centroid. So the first thing, as we just saw, so if you have multiple points that you want to compare, you need to create a multi-point object from them. And basically how we can create a multi-point object is to basically say that data, actually what we are doing is this kind of unary union. So what we say that data dot unary union. So what this will do is that it takes all those point objects and put them into a single feature. So we are doing just the same as before, but now we have basically, if we print out, so now we have a long list of points in here, and as you can see, we have a multi-point object. So this is really easy way of doing the same multi-point stuff that we just did manually before. And the second thing that we want to do, we were interested in the centroids, so of course we need to calculate the centroid for those polygons. So how we could do that? Well, I said that to this polys geodata frame, create a new column called centroid, and how we can calculate that was to just call this attribute called centroid, which will create and do, oh, not that one, dot head. So now we have the centroids here as point objects. So the original geometry is still here in the geometry column, and they are polygons, and here we have the centroids. So now we want to basically see what is the closest address to these centroids. And how we can do that is to take advantage of the function that was created and run that. So how we can do that? So what I'm interested in this addresses file is to have this ID. This is a short number which is quite and it can be used to make a table join afterwards. So this is a good kind of column to take and bring from that other data frame back to the polygon data frame. So let's take that and import and basically join that into our polygon data frame. So what I will do is that basically I said that this polys will have, and I will create a nearest ID. So this is the column that will be created to this polygon data frame, and then I just say that polus dot apply. So this is the function that can be used to run these and use these functions that we have self-made. And how we use this function was that the first parameter we said that what is the function that we use? Well, we use the nearest function. Then we need to specify for each one of these without any default value the parameters inside. So basically the geometric union parameter, which is this one here, well, that will get this variable unary union, which is the multipoint feature. So I said that geom union equals to unary union. Then the data frame 1, well, the data frame 1 here equals to the polygon here, polygon layer. So the polygons that we are dealing here, the data frame 2, so from where we are actually searching the information from, well, it is the data that has the addresses, and then what is the geometric column in this polygon layer. So remember that the polygon layer is the data frame 1, so we can specify that geometry 1 column equals not the geometry but actually the centroid, because we were interested in finding the nearest centroid. So let's say that geom1 column equals to, and the name of the column that we have, which is called centroid. And then one last thing, this is a bit complicated or more complicated function that we have here. We want to specify what is the source column, so what information will be actually drawn from the other data frame. And as I said, we were interested in getting this ID information from the other one. So we can say that source column equals to ID. Do this geometry CRC call. Oh yeah, good. Thanks. That would have raised an error. So yeah, indeed it needs to be the same as here. So it's source column and it needs to be the same. And then this geometry 2 column, we don't need to specify anything for that because the points are under the geometry here, so it is right one by default. One last thing that we still need to do is to specify again the axis direction, which is 1. So go row by row instead of column by column. And now finally, when we have defined all these different parameters, we are in a situation when we can actually run this thing, and let's hope for the best. It didn't take too long, but now what we should have is that we have this nearest ID from, so now each polygon has the ID from the nearest point of the other of those addresses points in here, and this can be quite useful in some cases. Now as we still have time, maybe in the materials I don't actually make any plots out of these, but maybe we could still plot the kind of line strings between the centroids and the points here. So what I will do, now this goes a bit experimental. Let's say what we have in here, we have columns. So in this polygon data frame we have these columns. What I want to do is that I want to take the columns and basically make a table join between this polygon and this point data frames. Because we have the same column called geometry in both of these. I want to basically, because I don't anymore need the polygons in this polygon data frame, I will drop that out, or maybe not drop, I will just rename it. So I will say that rename polygon geometry. So I will say that polys dot polys equals to polys dot rename columns equals to, and I said that geometry should be called polygeom. What is now? Is it with one? Sorry. This should be colon. Yeah. So now we should have description name polygeom centroid nearest ID. So what I want to do now is that I want to make a table join. So I want to have all the attributes from the data frame. So these points and the addresses back to the polygons. So I said that polys equals to polys dot merge. And how do we want to merge? So we have this common attribute now called ID, and we can basically say that I want to combine the data frames with the ID attribute, and that's it. Oh yeah, sorry. What we want to merge is of course the data and then on ID. Okay, data, that's columns. Yeah, polys dot columns. It was, yeah, okay. So left on ID and right on nearest ID. So it had a different name. Still something. No, it was other way around. Nearest ID and ID. Okay, finally. So now we should have all the information in the same data frame. So now what I want to do is to basically create a line string geometry between the centroid and the geometry in the other data frame, which is now combined into the same one. So what I want to do is that I want to still import the line string from here. This is something that you needed to do in the exercise, so this is maybe something good to take a look at. So create a line string from the centroids and the address points. So let's do so that let's create a new attribute called line. Let's just make it empty, and then let's say that polys line equals to, and then we use the apply function. So again, this is now something maybe a bit more advanced, but how many of you, I don't know if I have showed this before, how many of you have used or saw this function called lambda? Yeah, this is something quite handy. You can do nice one-liners in a way that you basically feed a function inside here. what I will do is that I will just create it first and then I explain a bit. So we create this lambda row. So this is basically similar to that you would be iterating over rows, and basically this row will include data, and for each row we have this column called geometry, which is basically this line. So this is the original address point, and then we have another column with another point called centroid. So this is the centroid of the polygon where we started from. So now we have these two objects, or 2 point objects, and how we make a line out of them is that we put them inside a line string as a list. So basically we should create a list of points and insert them into that line string object. So this is nothing, can you see it? Yeah, this is just the same as you would create a line string, but now we are doing it inside here. So for each row we take the geometry of the first point object and the second one, and then we put them inside a list, which is this one. And then we close the first parenthesis, which is for this line string, and what we are altogether doing here is that we are actually iterating over these lines. The last thing that we want to do is to say that axis equals to 1, so that we go again row by row instead of column by column. So don't worry if you didn't get everything and it might be confusing. It might be easier to create a function, but I just wanted to show you because this is something that comes out every now and then, and these are quite actually nice nice things to use every now and then. But now what we can do is to execute this, and now we should have inside here a line string object between those centroids and those address points. One thing I still do is to, of course, visualize it so we can actually see a bit. I will just take the from the polygons only the line object, and maybe something else, maybe the ID, for example. So I just select those columns from the polygons like this, and now I should have lines data frame with the line string and the ID, nothing more. And then let's plot. Not like this. Okay, now it came out as a pandas data frame. Yeah, we want to create it as a GeoPandas data frame, so we can convert that pandas data frame into geodata frame just by like this, and then we can say that CRS equals same to polish.crs. And now let's see what is the type of our data frame. Now it's a geodata frame. Let's see what we have now. We can give the color of the line, for example, as the ID. So each ID will be with different colors. Yeah. No, oh yeah. One thing that we still need to do. So we need to rename the line, because now the geometry, the name of the geometry in our data frame is line, so we actually need to say that the column is geometry instead of that. So we can say that lines.columns equals to geometry and ID. So now finally you should, so now we have a geometry ID. Now I just want to make sure that this geodata frame comes out correctly. So we also specify what column contains the geometry. It should be able to take whatever column name, but at least in the earlier versions of GeoPandas it hasn't worked, so that's why I always change the name to geometry. Let's now check. It's geodata frame. Then fingers crossed. Finally. So here we are. So now we actually can see which one of those points that we, well, they are somewhere here. Which one of those, well, doesn't matter. So some of those points, those addresses that we geocoded in the beginning of the lesson, so those, which one of those is the closest point to each centroid of those polygons that we had. So those polys, I don't try to plot that because the information is different already. But this is how you can do line geometries in inside a geodata frame quite easily, which is nice. And this is indeed something that was kind of one of the problems in exercise 2 last week. Okay, that's all and some extra for this week. Let's still go through the exercise number 3. So again, I have something fun for you. So what we are doing this week is kind of similar to what we did during the lesson. So the basic idea is to find out in our study region, so in Helsinki region, how many people lives within 5 kilometers distance from big shopping centers. So this is really typical kind of question that the kind of entrepreneurs of any shops are needing. So what is the potential amount of customers that I can reach from certain region? So that's kind of the motivation behind here. And basically what you should do, so I provide you, oh yeah, I don't provide you, you need to do it yourself. So you need to find the addresses for 1, 2, 3, 4, 5, 6. So 6 different shopping centers in the region, and put them into this shopping centers.txt file. And basically you should use the same formatting as in the lesson materials. And then what you need to do is to geocode the addresses so that you have those shopping centers in a map. Then what you need to do is to reproject the data, because by default they are latitude and longitude, but we want to have the distance as meters. So reproject that into this projection, which is metric projection system. And then you need to make a buffer with 5 kilometers, which is the problem 2. So it kind of continues from there. And when you have created the buffer, you can do spatial join with the population grid that we used in the lesson material, and what we want to calculate is the sum of people that kind of are within that 5 kilometer buffer zone. And that's basically the idea here. And then, well, this could have been extra, but I decided to put it as an obligatory, just that you can get a practice, but it should be easy. So kind of the one that kind of practicing the closest, the nearest analysis that we just did. So what you should do here is to basically create another text file called activity locations. There you should put the address of your work and home location. You don't need to put your real work and home location, but you can. But it can be whatever location in Helsinki region. And then the idea is to find out which one of those shopping centers that you geocoded in problem 1 is the closest one to you at home, and which one is the closest one in the workplace. So those are the 4 problems for this week. Then there are some, you should write the answers, like how many people live within 5 kilometers from each of these shopping centers. So write the answers here, but also your code should you should print it out in the code so that